Due to low salinity of freshwater, animals face the problem of osmoregulation. Because the salt concentration of body fluids of animals remain higher than the freshwater, hence, the water continuously tend to enter the body which should be readily removed. Most aquatic animals, e.g., protozoa and fishes, have the means to excrete extra amount of water of body by osmoregulation. For this purpose, protozoa employ contractile vacuoles and other multicellular invertebrates and chordates use excretory organs, such as nephridia, kidney, etc. Figure 11.1. Osmoregulation in A. Freshwater fish and B. Marine fish. 8. 4 hydrogen ion concentration. In freshwater environments, pH is a determining factor for the biota by becoming a limiting factor. The pH value of different freshwater bodies may fluctuate seasonally and annually. The pH of surface waters and deeper waters exhibit marked differences. Srinivasan, 1968, has reported a marked pH variation of 2.2 units between surface water and deeper water in the Sandinal Reservoir in the Nilgiris, India. Though pH range is species-specific, yet lower aquatic forms in general showed little reaction to alterations in pH, while higher aquatic organisms, e.g., fishes, responded quickly to little pH variations. Lentic ecosystems. Lentic ecosystems include all standing water, freshwater habitats such as lakes, ponds, marshes, swamps, bogs, meadows, etc. Some of the important lentic ecosystems or wetlands have been tabulated in Table 11-1. J. 10. Ill classification of wetlands or lentic ecosystems, excluding lakes and ponds, Smith 1974. A. Inland freshwater areas. 1. Seasonally flooded soil covered with water or waterlogged during variable periods but well drained during much of the growing season. In upland. Depression bottomlands. Bottomland hardwoods 2. Herbaceous growth. 2. Freshwater meadows without standing water during growing season, waterlogged to within few inches of surface. Grasses, rushes, sedges. Broadleaf plants. 3. Shallow freshwater marshes, soil waterlogged during growing season, often covered with about 15 centimeters or more of water. Grasses, bulrushes, spike rushes. Cattails, arrowhead, smartweed, pickerelweed. A major waterfowl production area. 4. Deep freshwater marshes, soil covered with 15 centimeters to 91 centimeters of water. Cattails, reeds, bulrushes, spike rushes, wild rice. Principal duck breeding area. 5. Open freshwater marshes, water less than 3 meters deep, bordered by emergent vegetation, pondweed, naiads, wild celery, water lily. Brooding, feeding. Nesting areas of ducks. 6. Shrub swamps, soil waterlogged, often covered with 15 centimeters or more water. Alder, willow, buttonbush, dogwoods. Ducks nesting in. Feeding to limited extent. 7. Wooded swamps, soil waterlogged, often covered with 30 centimeters of water. Along sluggish streams, flat uplands, shallow lakes, basins. North of USA, tamarack, arborvitae, spruce, red maple, silver maple. South of USA, water oak, overcup oak, tupelo, swamp black. Gum cypress. 8. Bog soil waterlogged, spongy covering of mosses. Heath shrubs, sphagnum, sedges. B. Coastal freshwater areas. Shallow freshwater marsh, soil waterlogged during growing season, at high tides as much as 15 centimeters of water on landward side, deep marshes along tidal. Rivers, sounds, deltas, grasses and sedges. Important waterfowl areas. 10. Deep freshwater athi tide covered with 15 centimeters to 1.8 meters of water. Along tidal. Rivers and bays, cattails, wild rice, giant cutgrass. 11. Open freshwater, shallow portions of open water along fresh tidal rivers and sounds. Vegetation scarce or absent. Important waterfowl areas. 1. Lakes and ponds. Lakes are inland depressions containing standing water. They may vary in size from small ponds of less than a hectare to large seas covering thousands of square kilometers. They may range in depth from a few centimeters to over 1666 meters. Ponds, however, are considered as small bodies of standing water so shallow that rooted plants can grow over most of the bottom. Most ponds and lakes have outlet streams and both are more or less temporary features on the landscape because their filling is inevitable. The aquatic habitats of lake and pond remain vertically stratified in relation to light intensity, wavelength absorption, hydrostatic pressure, temperature, etc. In a lake, for example, there are 3 well-recognized horizontal strata, namely, I. Shallow water near the shore forms the littoral zone. It contains upper warm and oxygen-rich circulating water layer which is called epilimion. The littoral zone includes rooted vegetation. E. Sublittoral zone extends. Lake surface. 6 meters. Littoral zone registered 10 meters. Sublittoral zone. Profundal zone compensation level equals no photosynthetic organism. Figure 11.2. Different zones of a deep freshwater lake. From rooted vegetation to the non-circulating cold water with poor oxygen zone, i.e., hypolimion. E. Limnetic zone is the open water zone away from the shore. It ice zone up to the depth of effective light penetration where rate of photosynthesis is equal to the rate of respiration. IV profundal zone is the deep water area beneath limnetic zone and beyond the depth of effective light penetration. V. Abyssal zone is found only in deep lakes, since it begins at about 2,000 meters from the surface. Ponds have little vertical stratification. In them, littoral zone is larger than the limnetic zone and profundal zone. In a small pond, the limnetic and profundal zone are not found. Lakes, thus, differ from ponds in having relatively larger limnetic zone and profundal zone than littoral zone. Further, lentic water of a lake or pond is also classified on the basis of the depth of light penetration enabling photosynthesis into tryptogenic zone, includes littoral plus sublittoral zones, and a trypholytic zone, upper part of profundal zone. The former is often distinguished by abundant plant growth and dependent fauna, while the latter denotes a general absence of vegetation and harbors mostly saprobes. In between the two zones. Ice compensatal OEBNL. Which forms a boundary between two zones. It exhibits perfect equilibrium between respiration and photosynthesis. Physico-chemical properties of lakes and ponds. Lakes have the tendency to become thermally stratified during summer and winter too. Littoral zone F1. FL. SN. N. Equals limnetic zone equals N profundal zone. Figure 11.3. Different zones of a freshwater pond. Undergo definite seasonal periodicity and depth distribution of heat and oxygen. Light too penetrates only to a certain depth, depending upon turbidity. These gradations of oxygen, light and temperature profoundly influence the life in the lake, its distribution and adaptation. Kinds of lakes. Different classifications of lakes on the basis of physical factors, productivity, etc. exist. Based on temperature, Hutchinson, 1957, classified lakes into dimictic, monomictic and polymictic lakes. The dimictic lakes exhibit two overturns every year. While monomictic lakes may be cold monomictic and warm monomictic, the former being characterized by a circulation only during summer, while the latter has a complete circulation in winter as well. Polymictic lakes present circulations throughout the year. Based on the humic acid contents, the lakes of world have been classified into clear water lakes and brown water lakes. Brown water contains high humus content. Clear water lakes may be divided into two types: the oligotrophic type, whose water is poor in nutritive plant material and shows nearly equal distribution of oxygen during summer and winter months and whose mud bottom contains little organic material, and the eutrophic type, which is rich in nutrients. At greater depth below the thermocline in summer, eutrophic lakes show a considerable reduction in oxygen content and their mud bottom is composed of typical muck. Eutrophic lakes are polluted lakes and support the growth of the microorganisms. With regards to above features, an intermediate type of lake is called mesotrophic lake, C-1993. Special types of lakes. There also occur the following 5 types of lakes. 1. Dystrophic lakes. These lakes contain high concentration of humic acid in water. The margins of these lakes have a low pH and develop into peat bogs. 2. Deep ancient lakes. Lake Baikal in Russia is the most famous of ancient lakes. It is the deepest lake in the world. This lake is often nicknamed as Australia of freshwater, since it contains various unique animals. It contains about 384 species of arthropods, 98% of which are endemic, i.e., found nowhere else. Likewise, 81% of its 36 species of fish are also endemic. 3. Desert salt lakes. These lakes exist in sedimentary drainages in arid climates where evaporation exceeds precipitation, e.g., Great Salt Lake of Utah, USA. Biotic community of these lakes comprises only those species which can tolerate high salinity, e.g. Biotic community of the polymic polymictic aquatic ecosystems are the source of life on Earth. Aquatic ecosystems. Freshwater communities. The habitat approach describes the distinctive feature kinds of lakes. Different classifications of lakes on the basis of physical factors, productivity, etc. exist. Based on temperature, Hutchinson, 1957, classified lakes into dimictic, monomictic and polymictic lakes. The dimictic lakes exhibit two overturns every year. While monomictic lakes may be cold monomictic and warm monomictic, the former being characterized by a circulation only during summer, while the latter has a complete circulation in winter as well. Polymictic lakes present circulations throughout the year. Based on the humic acid contents, the lakes of world have been classified into clear water lakes and brown water lakes. Brown water contains high humus content. Clear water lakes may be divided into two types: the oligotrophic type, whose water is poor in nutritive plant material and shows nearly equal distribution of oxygen during summer and winter months and whose mud bottom contains little organic material, and the eutrophic type, which is rich in nutrients. At greater depth below the thermocline in summer, eutrophic lakes show a considerable reduction in oxygen content and their mud bottom is composed of typical muck. Eutrophic lakes are polluted lakes and support the growth of the microorganisms. With regards to above features, an intermediate type of lake is called mesotrophic lake, C-1993. Special types of lakes. There also occur the following 5 types of lakes. 1. Dystrophic lakes. These lakes contain high concentration of humic acid in water. The margins of these lakes have a low pH and develop into peat bogs. 2. Deep ancient lakes. Lake Baikal in Russia is the most famous of ancient lakes. It is the deepest lake in the world. This lake is often nicknamed as Australia of freshwater, since it contains various unique animals. It contains about 384 species of arthropods, 98% of which are endemic, i.e., found nowhere else. Likewise, 81% of its 36 species of fish are also endemic. 3. Desert salt lakes. These lakes exist in sedimentary drainages in arid climates where evaporation exceeds precipitation, e.g., Great Salt Lake of Utah, USA. Biotic community of these lakes comprises only those species which can tolerate high salinity, e.g., Artemia brine shrimp. 4. Desert alkali lakes. These lakes occur in igneous drainages in arid climates, e.g., Pyramid Lake, Nevada, USA. High pH and concentration of carbonates are the characteristic features of these lakes. 5. Volcanic lakes. Acid or alkaline lakes associated with volcanic regions are called volcanic lakes, e.g., Japanese and Philippine lakes. In these lakes exist the extreme chemical conditions. Types of ponds. Ponds 2 are of the following 4 types. I. Floodplain ponds. These are ponds which are found in stream floodplains. These are quite productive habitats due to accumulation of organic matter in them. E. Temporary ponds. These ponds remain dry for most part of the year but support a unique community. Organisms in such ponds must be able to survive in a dormant stage during dry periods or be able to move in and out of ponds. E. Artificial ponds. These ponds are the result of damming of a stream or basin by man. They are artificially managed habitats. IV. Beaver ponds. Ponds constructed by beavers equals amphibious rodents are called beaver ponds. The beaver often does not construct pond but live in holes in the bank of streams and, thus, becomes essentially the stream animals. Origin of lakes and ponds. Lakes and ponds arise in many ways. For example, North American lakes were formed by glacial erosions and deposition and a combination of the two. Glacial abrasions of slopes in high mountain valleys and grave basins, which filled with water from rain and melting snow to produce tarns, i.e., small mountain lakes. Retreating valley glaciers left behind crescent-shaped ridges of rock debris, which dammed up water behind them. Lakes are also formed by the deposition of silt, driftwood, and other debris in the beds of slow-flowing streams. Craters of extinct volcanoes may fill with water and landslides can block off streams and valleys to form new lakes and ponds. Further, man intentionally creates artificial lakes by damming rivers and streams for power, irrigation, and water storage, or by constructing small ponds and marshes for water, fishing and wildlife. Man-made lakes are often called impoundments. They may be a close type or open type depending on the discharge of water into it. Sandinella is a closed impoundment, while Picara is an open impoundment. Srinivasan, 1957. Impoundments differ from natural lakes in thermal and oxygen variations and are often characterized Impoundments differ from natural lakes in thermal and oxygen variations and are often characterized by a low percentage of bottom dwellers or benthos. Ponds occur in moss regions of adequate rainfall. Temporary ponds, which are often shallow and quick drying, contain a characteristic lentic environment. Permanent ponds contain water throughout the year, while floodplain ponds are formed when a stream shifts its position, leaving the formed bed isolated as a body of standing water. Biotic communities of lakes and ponds. Different organisms of the lentic environment can be ecologically classified based on whether they are dependent on the substratum or free from it. Organisms depending on the substratum are called pedonic forms, and those that are free from it are the limnetic forms. Further, the aquatic organisms may also be classified into following groups depending upon their sizes and habits. 1. Neuston. These are unattached organisms that live at the air-water interface. They may include floating plants such as duckweed, as well as many types of animals. Animals that spend their lives on top of the air-water interface, such as water striders, are termed apneuston, while others, including wind, N, G, E, N, R, S, S, U. Certain animal planktons or zooplanktons are exceedingly active and move relatively great distances considering their small. Insects such as diving beetles and back swimmers, which spend most of their time on the underside of the air-water interface and obtain much of their food from within water, are termed hyponeuston. 2. Plankton. These are forms which are found in all aquatic ecosystems except for fast-moving rivers. They are small plants and animals whose powers of self-locomotion are so limited that they cannot overcome currents. Thus, their distribution is controlled largely by the currents in their ecosystems. Most planktons, phytoplanktons, and zooplanktons can move a bit, however, either to control their vertical distribution or to seize prey. Certain animal planktons or zooplanktons are exceedingly active and move relatively great distances considering their small size, but they are so small that their range is still controlled largely by currents, and such planktons are also known as nectoplankton. 3. Nekton. Nectinic animals are swimmers and are found in all aquatic systems except for fastest-moving rivers. In order to overcome currents, these animals are relatively large and powerful. They range in size from the swimming insects of quiet water, which may be only about 2 millimeters long, to the largest animal that has ever lived on Earth, the blue whale. 4. Benthos. The benthos include the organisms living at the bottom of the water mass. They occur virtually in all aquatic ecosystems. The benthos organisms living above the sediment-water interface are termed benthic epifauna, and those living in the sediment itself are termed infauna. Neustons of lentic aquatic environment. The water surface of lake or pond contains certain free-floating hydrophytes such as Wolffia, Lemna, Spirodella, Azolla, Salvinia, Pistia, and Eichhornia. These plants remain in contact with water and air, but not soil. Biota of littoral zone. Lentic aquatic life is most prolific in the littoral zone. The littoral zone of a lake remains rich in pedonic flora, especially up to the depth to which effective light penetration is possible, facilitating the growth of rooted vegetation. At the shore proper are the emergent vegetation, which remain firmly rooted in the shore substratum, but their tops with thin chlorophyll-bearing regions are exposed. Certain rooted emergent plant species of littoral zone are ranunculus, monocoria, cypress, and rumix. Interspersed with these plants are the cattails, typha, bulrushes, sherpus, arrowheads, sagittaria, and pickerel weeds. Slightly deeper air. The rooted plants with emergent plants floating leaves such as the water lilies, nymphaea, nelumba, aponogeton, trappa, and marsilea. Still deep earth littoral zone of lake or the agile typf, a 2 thin stemmed water, n. Weeds, rooted but totally bulrush. Submerged. Such a submerged vegetation sagittaria, includes plants such as Alodia, Vallisneria, water lily empyreophyllum, isotes, ELLLD, hydrilla, chara. Potamogeton, etc. Fig.11.4. Flora of the lentic habitat. Floating plants. Submerged plants. Dash. 1e. The phytoplankton of littoral zone. The phytoplankton of littoral zone of lake is chiefly composed of diatoms, e.g. Navicula, Cyclotella, blue-green algae, e.g. Microcystis, Oscillatoria, green algae, e.g. Cosmarium, Storostrum, and Holophytic. Flagellates. Srinivasan, 1970, has. Pond snail Disticus amphi pod mosquito observed the abundance of mari. Nay. Climbing dragonfly, damselfly nymphs, rotifers, brachionis flatworms, bryozoa, hydra, snails, limnia, and other. With the exception of a few rotifers such as Caratella, Brachionis, Diarella, and Trichocerca, and crustaceans such as Cyclops, Daphnia, and Moina, most freshwater animals of lentic habitat depend in one way or other on the aquatic vegetation. Larvae of Chironomus are found underneath the leaves of floating plants. The zooplankton of littoral zone consists of water fleas such as Daphnia, rotifers, and ostracods. The free-swimming fauna Nekton includes Paramecium, Euglena, Ranitra, Coryxa, Didiscus, larvae of Culex and of Chalboris, Geris, Gyrus. Larvae of Chironomus are found underneath the leaves of floating plants. The zooplankton of littoral zone consists of water fleas such as Daphnia, rotifers, and ostracods. The free-swimming fauna Nekton includes Paramecium, Euglena, Ranitra, Coryxa, Didiscus, larvae of Culex and of Chalboris, Geris, Gyrinus, etc. Among the vertebrates, frogs, salamanders, snakes, and turtles are the Nektons of littoral zone. Floating members of the community Neuston or were beetles, water spiders, and numerous protozoa. Many pond fishes such as sunfish, top minnows, bass, pike, and gar spend much of their time in the littoral zone. Biota of limnetic zone. Limnetic zone is the region of rapid variation, with the water level, temperature, and oxygen content varying from time to time. In certain Himalayan lakes which have a glacial origin, change in water level is a conspicuous phenomenon, the onset of summer bringing forth a rapid and sudden rise in water level. Various protozoans which are capable of encystment during adverse ecological conditions, tardigrades such as Macrobiotis, rotifers such as Rotaria, Phylodina, copods, snails, and frogs occupy the limnetic zone. Sedentary and slow-moving forms are excluded from this zone because of predators and lack of permanent substratum for attachment. Many microscopic plants, volvox, Euglena, and fishes also occupy this zone. The limnetic zone has autotrophs in abundance. Biota of profundal zone. The deep profundal life consists of bacteria, fungi, clams, bloodworms, larvae of midges, annelids, and other small animals capable of surviving in a region of little light and low oxygen. In the profundal zone, autotrophs cannot produce food, and the main source of energy is detritus that rains out of the limnetic zone. All the organisms of this zone are heterotrophs, either as detritus feeders or as carnivores. Most of our largest lake fishes inhabit the dark waters of hypolimnion for most of their lives. In addition to detritus from the limnetic zone, food washed into lakes by rivers can settle out and serve as food for profundal animals. Benthos of lake bottom. The lake bottom in young lakes may be of the original rock. In older lakes, it will have been covered with sediment to form a uniform substrate of mud or sand. The benthos community includes several species of insect larvae, including those of small mosquitoes such as midges, burrowing mayflies, clams, snails, and tubeworms. Distribution of oxygen and dissolved nutrients in lakes. The productivity of a lake depends on the amounts of oxygen and available nutrients dissolved in the water. As a general rule, the littoral zone behaves as a normal ecosystem, with oxygen being produced by photosynthesis within the community, as well as being constantly mixed into the water at the surface. Productivity within the littoral zone is directly controlled by the nutrient cycling within the littoral zone ecosystem, and biogeochemical cycles apparently operate as do in terrestrial ecosystems, with sediments serving as a storage place for inorganic nutrients such as phosphate, and some rooted plants being able to draw nutrients out of the sediments through their roots. McCroy and Barr State, 1970. But in the pelagic zone, limnetic and profundal zones, the distribution of oxygen and nutrients is exceedingly uneven. But in the pelagic zone, limnetic and profundal zones, the distribution of oxygen and nutrients is exceedingly uneven, and this has a profound effect on the behavior of the lake as a whole, especially in those whose pelagic zone is much larger than the littoral. The epilimnion of a lake is typically well oxygenated, both because of the production of photosynthetic oxygen in the epilimnion and because of the oxygen uptake at the surface. The amount of nutrients dissolved in the water is highly variable, mainly because most of the nutrients in the epilimnion have been incorporated into living tissue. Thus, production of epilimnion is controlled by amount of available nutrients, which, in turn is controlled primarily by the rate of cycling within the epilimnion, the rate of loss to the hypolimnion of nutrient-rich detritus, and the rate of return of soluble nutrients from the hypolimnion during overturn. The fact that only heterotrophic metabolism proceeds in the hypolimnion means that the level of production is determined by the amount of detritus raining into it. As the decomposition of detritus releases soluble nutrients, therefore, there is an inverse relationship between oxygen concentration and concentration of vital nutrients. It is paradoxical that the greater the productivity of a lake, the lower the oxygen concentration in its hypolimnion. For example, oligotrophic lake, which is virtually sterile biologically, has low production but its water remain well saturated with oxygen from top to bottom, orthograde oxygen curve. Likewise, a eutrophic lake has high productivity, but there is substantial oxygen depletion from top of the hypolimnion to the bottom, with depletion most extreme in the bottom layers, clinograde oxygen curve. However, in most lakes, oxygen is thoroughly mixed and is essentially at saturation during overturn. Lotic ecosystems. Running or moving water are lotic ecosystems, include rivers, streams, and related distribution of oxygen and dissolved nutrients in lakes. The productivity of a lake depends on the amounts of oxygen and available nutrients dissolved in the water. As a general rule, the littoral zone behaves as a normal ecosystem, with oxygen being produced by photosynthesis within the community, as well as being constantly mixed into the water at the surface. Productivity within the littoral zone is directly controlled by the nutrient cycling within the littoral zone ecosystem, and biogeochemical cycles apparently operate as do in terrestrial ecosystems, with sediments serving as a storage place for inorganic nutrients such as phosphate, and some rooted plants being able to draw nutrients out of the sediments through their roots. McCroy and Barr State, 1970. But in the pelagic zone, limnetic and profundal zones, the distribution of oxygen and nutrients is exceedingly uneven, and this has a profound effect on the behavior of the lake as a whole, especially in those whose pelagic zone is much larger than the littoral. The epilimnion of a lake is typically well oxygenated, both because of the production of photosynthetic oxygen in the epilimnion and because of the oxygen uptake at the surface. The amount of nutrients dissolved in the water is highly variable, mainly because most of the nutrients in the epilimnion have been incorporated into living tissue. Thus, production of epilimnion is controlled by amount of available nutrients, which, in turn is controlled primarily by the rate of cycling within the epilimnion, the rate of loss to the hypolimnion of nutrient-rich detritus, and the rate of return of soluble nutrients from the hypolimnion during overturn. The fact that only heterotrophic metabolism proceeds in the hypolimnion means that the level of production is determined by the amount of detritus raining into it. As the decomposition of detritus releases soluble nutrients, therefore, there is an inverse relationship between oxygen concentration and concentration of vital nutrients. It is paradoxical that the greater the productivity of a lake, the lower the oxygen concentration in its hypolimnion. For example, oligotrophic lake, which is virtually sterile biologically, has low production but its water remain well saturated with oxygen from top to bottom, orthograde oxygen curve. Likewise, a eutrophic lake has high productivity, but there is substantial oxygen depletion from top of the hypolimnion to the bottom, with depletion most extreme in the bottom layers, clinograde oxygen curve. However, in most lakes, oxygen is thoroughly mixed and is essentially at saturation during overturn. Lotic ecosystems. Running or moving water are lotic ecosystems, include rivers, streams, and related environments. They are remarkably variable, ranging in size from Ganga, Yamuna, Hindon, Kali Nadi, Sutlej, Gomti, Brahmaputra, Narmada, Mahanadi, Kabri, Krishna, Godavari, etc., to the trickle of a small spring. They vary from raging torrents and waterfalls to rivers whose flow is so smooth as to be almost unnoticeable. A given river varies considerably over its length, as it changes from a mountain brook to a large river. This is most noticeable in the abiotic factors of the environment, but all features of the ecosystem vary in response. Characteristics of lotic environment. Moving waters differ in the three major aspects from lakes and ponds. Current is a controlling and limiting factor. Land-water interchange is great because of the small size. Moving waters differ in the three major aspects from lakes and ponds. Current is a controlling and limiting factor. Land-water interchange is great because of the small size and depth of moving water systems as compared with lakes, and oxygen is almost always in abundant supply except when there is pollution. Temperature extremes tend to be greater than in standing water. Besides these, the most distinctive features of moving water ecosystems are those related to their motion, i.e., the rate of flow and the stream velocity. The rate of flow or discharge refers to the volume water passing a given observation point during a specific unit of time. It is measured in units such as m sec, featuring *sec, or acre-feet sec. 1 acre-foot is equivalent to a volume of water 1 acre in area by 1 foot deep. It tends to increase steadily growing downstream, as tributaries join with the main river. The velocity of flow is the speed at which the water moves, and is measured in m/sec, featuring sec, or mi, per hour. Velocity is variable, but it also tends to increase downstream with increasing discharge. A factor that may be even more important to the biotic community is the turbulence, or the irregularity of the motion of the water particles. Perfectly even flow, in which water particles move parallel to one another, is called laminar flow. It is contrasted with turbulent flow, in which the movement of water particles is highly irregular. In highly turbulent water, the erosive power is great, the shear forces at the water-sediment interface at the bottom of the river are powerful, and the amount of oxygen incorporated into the water is very high. In streams with laminar flow, the erosive power is lower, the shear forces at the bottom of the stream are lower, and relatively less oxygen is incorporated into the water than turbulent waters. The moving water ecosystems can be divided into following two ecosystems depending upon the velocity and rate of flow of water body. 1. Rapidly flowing water, and 2. Slowly flowing water. A. Rapidly flowing water. Rapidly flowing water, of fast-moving torrential streams, etc., can be defined as the portion of the stream in which the flow is both rapid and turbulent. Everything that is not attached or weighted is swept away by the current. This includes organisms and sediment particles alike. The substrate tends to be rock or gravel, and the fragments are rounded and smoothed by the water. The habitat itself is an extremely diverse one. Physical parameters such as shear force and rate of water movement tend to be quite different on top of a rock fragment, between rock fragments, or beneath rock fragments, and different species can exploit these differences in microhabitats. Aquatic plants, in addition, provide microhabitats for some torrential animals. The rarely occurring phytoplankton of rapid or riffle zone of stream includes diatoms, blue-green and green algae e.g., cladophora, eulithrix, and water moss e.g., fontanellus. 1. Plant inhabiting torrential forms. Some animals of rapidly flowing water streams live among the mosses and flowering plants such as Eriocolonizerum, Hydralium lichenoides, and Ecology. Animals inhabiting these plants have a torpedo-like body which enables them to offer minimum resistance to the current. Some animals such as funnel-mouthed tadpoles of megaliferous and ticulid larvae live entangled in the roots of these plants. They possess devices for fixation and have hydrostatic organs. Some animals such as cephalopteryx, helodes, Phylacrocera, Gammarus, etc., live among leaves and stems of aquatic plants. All these animals possess hook-like structures on their body helping them in anchoring on leaves and stems. The larvae of simulids and chironomids, however, live on the exposed surfaces of plants. 2. Rock inhabitant forms. The animals that live on the tops of exposed rocks have an efficient mechanism for staying in one place, otherwise, they will be swept away. The organisms in this microhabitat are universally flattened. Some, like the freshwater limpet, Pharisea, are virtually flat, offering others, such as water penny, the larva of the riffle beetle, and Baetis larva, are not only almost flat, but each of their legs possesses hooked claws that enable them to hold onto the substrate more firmly. Larvae of simulium and chironomids cling to rock top by grappling hooks at the posterior end of the body. Caddisfly worms contain both of these structures, claws on legs and hooks at posterior end of body. The mayfly nymphs iron and sphenus attach themselves to the rocks by means of functional pads. Some animals, including freshwater sponges, actually cement themselves to the surface of the rocks. Others, such as caddisflies, build houses out of sediment or wood fragments, which are then cemented firmly to the rocks. Exposed surfaces of rocks also contain few sessile algae and few plants. A significant amount of organic detritus is washed into rapid water ecosystems from upstream and adjacent terrestrial areas, however. This is the source of the most of energy in fast water ecosystems, and is much more important as an energy source than primary production within the stream itself. In consequence, the majority of primary consumers of such a microhabitat are detritus eaters. And have forms of spaces between rocks. Numerous different kinds of animals live in the spaces between the rocks. Many of them, such as mayfly and stonefly naiads, are flattened and have certain behavioral adaptations to hold them in place. These include thigmotaxis, by which they cling instinctively to any hard surface such as rock or another insect larva. Rheotaxis, by which the animals orient themselves to face into current and move upstream, is another adaptation of this sort. In many of these naiads, the combination of the organism's shape and behavior is such that the current presses the insect tightly against the rock, increasing the friction between the animal and its substrate. Other insect larvae, such as the helgramite, are large and covered with spines. Their size make it somewhat harder for the current to sweep them away, while the spines help in holding the larva in places between stones. 4. Inhabitants occurring beneath rocks. Many species such as flatworms, annelid worms, other insect larvae, clams and some species of snails, live beneath the rocks. The current is weaker here, and animals are less likely to be carried away. They lack any special adaptation. Finally, if the current is sufficiently slow, certain swimming organisms such as fish will be present. The fish of fast water ecosystems tend to be stenothermal cold water fish, such as trout. The fishes of fast water ecosystems have small body size and streamlined body. Trout and mashare are capable of moving against the current or waterfall by muscular effort. Majority of torrential fishes, however, live on or among rocks and boulders, over which water flows very swiftly. Small loaches, Nomachilus, or loach-like fishes, Ambiceps alura, are met with at the bottom, and limpet-like fishes, e.g., Glyptosternum, Ballatora, or fishes with special modifications, Gara, Glyptosternum, Ballatora, occur on the rocks. The loaches and carps adhere to rocks like the limpets, with the ventral surface, inclusive of paired fins forming one large sucker, e.g., Gastromizone of Borneo, the Indian loach Ballatora of the eastern Himalayas and Assam hills, Hora, 1947. Physico-chemically, the fast water ecosystems resemble with cold, deep lakes. Water temperatures tend to be quite low, productivity is also quite low, and diversity is high. In the fast water ecosystem, the main control of productivity is the current, which seriously limits the amount and type of autotrophs production that can take place. B. Slowly flowing water. A slowly flowing water ecosystem is a very different type of system from the fast streams. Because the flow ice spots slower and more likely to be laminar, the erosive power of the stream is greatly reduced, and smaller sediment particles, silt, and decaying organic debris, instead of being carried away by the stream, are deposited on the bottom. In addition to these, the slow streams have a higher temperature. Consequently, planktonic organisms, especially protozoans, occur in large numbers in this ecosystem. The detritus-feeding benthos of slow water ecosystems include those which either live on the bottom, such as isopods, sobugs, mollusks, Sphaneus, Pisidium, and Anodonta, Dominata, and mayfly and damselfly naiads, or which burrow into the sediment, such as tubeworms, naiads of the burrowing mayflies, Cialis alderfly, Midge chironomus, and several other insect larvae, as well as clams, nematodes, snails, and rotifers. Swimming organisms are also abundant, including not only fishes, such as carps, catfishes, suckers, stingers, spoonbills, etc., which tend to be different species from those of fast water areas, but also larger crustaceans such as amphipods, fast water shrimps. Finally, several insects spend most of their time at the surface of the stream. These include forms such as water striders, water boatmen, backswimmers, and predaceous diving beetles. Zooplankton is abundant, including a rich assemblage of protozoa and smaller crustaceans such as Cladocera, water fleas, and copepods. The richness of food afforded by slow streams attract a large number of reptiles, water snakes, crocodiles, turtles, and amphibians. Plant life is also abundant in a slow water ecosystem. It includes rooted vascular plants such as pondweeds and grasses, firmly attached aquatic mosses, and large multicellular filamentous algae. Modal algae such as diatoms and flagellates may abound in the open water. In all, the primary productivity of slow water ecosystem is higher than that of the rapid water ecosystem, and the community is relatively less dependent on food materials from outside. Further, the detritus food chain consisting of organisms such as bacteria and fungi is much better developed in this community as the partially decomposed organic debris that comprises the main food source for these organisms collects in the mud bottom. In some slow-moving streams, in fact, the bottom muds contain more organic material than mineral fragments. In slow water streams, oxygen concentration remains main limiting factor. The high level of animal activity coupled with an active detritus food chain can withdraw a large amount of oxygen from water of a slowly moving stream. In addition, the low level of turbulence means that less oxygen is incorporated into the water at the surface. Thus, the dissolved oxygen content of a slowly moving stream is likely to be much lower than that of a fast-moving stream. This is commonly reflected in the fauna of the stream. Fishes tolerant of low oxygen levels such as carps and catfishes are the most common fishes in slow water, while species with high oxygen demands, such as trout, are found in fast water. RUAYNIO ENO 18 SNMN-DK 1. Classify the freshwater environment. Describe lentic ecosystem with habitat of marine fish. Aquatic ecosystems, estuaries and marine communities. Estuarine ecology. Aiders of all streams and rivers ultimately drain into the sea. The place where this freshwater joins the salt water is called an estuary. An estuary, L-astis, tide, is the wide lower tidal part of a river which is strongly affected by tidal action. Estuaries are the transitional zones, ecotones, between the sea and rivers and are the sites of unequological properties possessing a characteristic biological makeup. They are semi-enclosed coastal bodies of water that have a free connection with the open sea and within which seawater is measurably diluted with freshwater from rivers. Examples of estuaries are river mouths, coastal bays, tidal marshes, and water bodies behind barrier beaches. Not all rivers open into estuaries. Some simply discharge their runoff into the ocean. Estuaries differ in size, shape, and volume of water flow, all influenced by the geology of the region in which they occur. As the river reaches the encroaching sea, the stream-carried sediments are dropped in the quietwater. These accumulate to form deltas in the upper reaches of the mouth and shorten the estuary. When silt and mud accumulations become high enough to be exposed at low tide, tidal flats develop, which divide and braid the original channel of the estuary. At the same time, ocean currents and tides erode that coastline and deposit material on the seaward side of the estuary, also shortening the mouth. If more material is deposited than is carried away, then barrier beaches, island and brackish lagoons appear. Type of estuaries. Estuaries are classified in various ways depending on diverse criteria such as geomorphology, water circulation and stratification, and systems energetics. Thus, on the basis of geomorphology, estuaries include 1. Drowned river valleys, 2. Fjord-type estuaries, 3. bar-built estuaries, 4. Estuaries produced by tectonic processes, 5. River delta estuaries, etc. Based on water circulation and stratification, estuaries are classified as I. Highly stratified or salt wedge estuaries, E. Partially mixed stratified estuaries, E. Completely mixed or vertically homogeneous estuaries, and IV. Hypersaline estuaries. On the basis of the ecosystem energetics, the estuaries have been classified by Odom et al. 1969 as 1. Physically stressed systems of wide latitudinal range, 2. Natural Arctic ecosystems with isostress, 3. Natural temperate ecosystem with seasonal programming, 4. Natural tropical coastal ecosystems of high diversity, and 5. Emerging new systems associated with man. Physico-chemical aspects of estuaries. Current and salinity, both very complex and variable, shape life in the estuary, where the environment is neither freshwater nor salt. Estuarine currents result from the interaction of a one-direction stream flow, which varies with the season and rainfall, with oscillating ocean tides, and the wind. The salinity of estuaries varies vertically and horizontally and fluctuates amazingly between 0.5–0.35%. Due to low salinity, freshwater has a lower density than seawater, plus 1.00, as opposed to 1.03. Were there no tides in an estuary to mix fresh and salt water, the lighter freshwater would simply flow over the heavier seawater and dissipate in the ocean. However, the tidal action acts as a plunger to thoroughly flush the estuary and mix the fresh and salt water. This has several results. The water level in the estuary fluctuates regularly, unlike that of river. For this reason, the habitat that is covered at high tide and uncovered at low tide is a prominent one in the estuary, and has no analog in any purely freshwater ecosystem. Further, the salinity is exceedingly variable and may change by a factor of 10 over the course of a day at any location. At low tide, most of water passing through the estuary is fresh river water, and the salinity is correspondingly low. At high tide, most of the water may be of marine origin, and the salinity correspondingly high. Flow may be somewhat stratified, or mixing may be incomplete, and the salinity at any time may vary considerably from one location to another. The intensity of current, and, hence, of the degree of mixing, is a function of the intensity of the tides and of the river's flow rate. In other words, an estuary is an exceedingly variable environment. Further, salinity of estuaries remains highest during the summer and during periods of drought, when less freshwater flows into the estuary. It is lowest during the winter and spring, when rivers and streams are discharging their peak loads. No stenohaline organism, such as Echinodermata, Cephalopoda, and other mollusks could hope to survive in the estuaries. Likewise, no organism that could not tolerate strong currents and the turbid water that results from strong currents could live there. The temperatures in estuaries fluctuate considerably diurnally and seasonally. Waters are heated by solar radiation and inflowing and tidal currents. High tide on the mudflats may heat or cool the water, depending on the season. The upper layer of estuarine water may be cooler in winter and warmer in summer than the bottom, a condition that, as in a lake, will result in a spring and autumn overturn. Anyhow, all estuaries have high productivity. As estuaries' high productivity is exceeded among aquatic communities only by coral reefs. The reason is that although an estuary may be a harsh environment in some ways, it is not in others. Because versus water surface, a typical estuary is L. Pipe _. IA. It. E. W. L. Estuary. Shallow. The mechanism of nutrient concentration is very simple. Particulate nutrient material enters the estuary at its upper end, is carried seaward by the falling tide and is brought back through the estuary by the rising tide, and so on for several cycles. The length of time it takes from a nutrient particle to traverse the estuary is substantially greater than it would take for it to traverse a similar length of even the most slowly flowing river. Thus, the estuary acts as a nutrient trap, with an average nutrient level significantly higher than either the river or the sea that it connects. Likewise, the concentration of energy-rich organic materials remain high in estuaries. The primary result of the concentration of nutrients and fixed carbon is a very high level of production within the detritus food chain. This has two aspects. First, the nutrient material is broken down bacterially at a very high rate, and recycled back into soluble form. This allows a very high rate of gross primary production for estuarine plants. More important, perhaps, the amount of nutrient-rich organic detritus allows a level of productivity for detritus-eating animals much higher than could be maintained on the basis of the primary production by estuarine plants. Biotic communities of estuaries. Carriker, 1967, has classified the regions of estuaries into the head, where freshwater enters the estuary, upper, middle and lower reaches with increasing range of salinities, and the mouth with salinity nearly equal to the sea. He has also classified the animals inhabiting the estuarine region into oligohaline, 0.5 to 5%, mesohaline, 5 to 18% in the upper reaches, polyhaline, 18 to 25% in the lower reaches, 25 to 30% in the middle, and euhaline, 30 to 50% in the mouth of the estuary. Communities of estuaries are a mixture of endemic species and those which come in from sea. Krishnamurthy, 1963, in fact reported that the extent of penetration of the polychaetes, Marphisa gravely, Diopatra euaryabilis, Clymene insecta, Loimia medusa, Glycera embranchiata, Onuphis aramida into the Ajar estuary in Madras from the Bay of Bengal vary with varying salinities at constant temperatures. Furthermore, estuary being a transitional zone between the freshwaters and seas is an ecotone, therefore, typical estuarine forms are unique in their habitat. Thus, the estuarine community is a mixture of three components, the marine, the freshwater and the brackish water. However, the diversity of both freshwater and marine components reaches a maximum. Total diversity of the estuarine community is lower than that of either of the more normal environments. The number of interactions between species is not high and some estuarine populations may fluctuate greatly in size. The plant of the estuary are of four basic sorts: phytoplankton, marginal and marsh vegetation. The plant of the estuary are of four basic sorts: phytoplankton, marginal and marsh vegetation, mud-flat algae, and epiphytic plants growing on the marginal marsh vegetation. Because of the turbid water found in estuaries, phytoplanktons are normally uncommon. However, in Hooghly-Matla estuarine system in West Bengal, Gopalakrishnan 1971 has reported an abundance of phytoplankton. However, in Hooghly-Matla estuarine system in West Bengal, Gopalakrishnan 1971 has reported an abundance of phytoplanktonic forms. Several species of diatoms, Syndra, Navicula, Rhizostoma, Fragilaria, Asteriobella, Bidulphia, Planktoniella, Hemidiscus, Chaetoceros, Cyclotella, Stephanodiscus, Triceratium, several species of green algae such as Pediastrum, Spirogyra, Eudornia, Trigoma, Closterium, Zygoma, Pandorina, Volvox, Chlorella, and blue-green algae such as Microcystis, Oscillatoria, Anabaena, and Trichodesmus. Most estuarine algae are of marine origin. Further, the most significant estuarine plants are marsh grasses such as Spartina, Silicornia, and Sherpis, as well as some submerged filamentous algae such as Cladophora, Chara and Enteromorpha. Very few animals feed on these plants directly, but a very large amount is consumed as detritus. The estuarine animal communities include zooplanktons and other animals. For example, the planktonic animal forms of Hooghly-Matla estuary of India include flagellate protozoans such as Euglena, Ceratium, Paradinium, Noctiluca, other protozoans such as Diffluvia, Archella, Vorticella, rotifer species such as Branchionis, Caratella, Asplanchna, etc., copepodes such as Dioptimus, Pseudodioptimus, Cyclops and Paracalinus, cladocerans of the genus Bosmina, Bosmanopsis cereodaphnia, Moina, besides a number of isopods. Gopalakrishnan, 1971. All these forms remain confined to water and led a pelagic existence. The best known estuarine animals are detritus feeders such as oysters, Ostrea sp, of Lake Chilka clams, lobsters, and crabs. Several insect larvae, annelid worms, mollusks, enter the estuary from the freshwater, while most marine phytoplankton, crustacea, annelid worms, anemones and bryozoa enter an estuary from marine ecosystems. For example, out of 130 species of fishes and 30 species of prawns of Hooghly-Matla estuary, several fishes such as hilsa, harpodon, muggle, trachyurus, etc., migrate from sea into the mouth of the estuary to form important fish catches, while some such as polymonid prawns are freshwater inhabitants and come to live in estuaries. Ajar estuary of Madras coast is found rich in invertebrate and vertebrate fauna, IR and Panacar, 1937. The common invertebrates of this estuary are sea anemones, e.g., Phytocetes gangeticus, Phytocodipsis ormani, Stevensonatus ornata, Pelocetes exul, Bollicractus gopali, etc. Hermaphrodite nereids, e.g., Lycastus indica, the tubiculus polychaete Diopatra variabilis, the burrowing polychaete Marphisa gravely, the oligochaete Pontodilus vermidensis, the mysids Rhopalophthalmus egregius and Mesopodopsis orientalis, the crabs Euca annulipes, Euca triangularis, Neptunus pelagius, Scylla serrata. Varuna literata, Cesarma tetragonum, the hermit crabs, Clibinarius olivaceus and Clibinarius podavensis, and several mollusks, e.g., Ostrea arcanensis, Medilus undulatus, Meritrix casta, Cuspidaria cochinensis, Stenothyria blandfordiana, Amnicola stenothyroids, Potomides singulatus, Styliger gopali and Versitella leachi. The vertebrate fauna of Ajar estuary includes the fishes such as Etroplus maculatus, Etroplus suratensis, Acentrogobius vertipunctatus, Acentrogobius nali, Panchax parvis, Aplocylus melastigma, and mud skipper Periophthalmus colroyderi, and snakes such as Natrix piscator and Cerberus ringcops. Subsystems of estuaries. An estuary consists of several basic subsystems linked together by the ebb and flow of water that is driven by the hydrological cycle and the tidal cycle. Some of its main subsystems are the following. 1. Shallow water production zones. In these zones, the rate of primary production exceeds the rate of community respirations. The producers are reefs, seaweed or seagrass beds, algal mats and salt marshes. This system exports energy and nutrients to deeper waters of the estuary and adjacent coastal shelf. Being rich in diverse types of producers, these remain programmed for virtually year-round photosynthesis and derive benefit from tidal action in creating a subsidized fluctuating water level ecosystem. They have all the three types of producers such as macrophytes, e.g., seaweeds, seagrasses and marsh grasses, benthic microphytes and phytoplanktons. Certain significant macrophytes are Spartina, Zostera and Thalassia. Benthic algae grow on macrophytes, sessile animals, rocks, sand and mud. Some estuaries have distinct blooms such as red tides of large blooms of red pigmented dinoflagellates, i.e., Goniolix and Gymnodinium. 2. Sedimentary subsystems. These subsystems occur in the deeper channels, sounds equals straits, and lagoons in which respiration exceeds production and in which particulate and dissolved organic matter from the production zone is used. In these habitats, nutrients are regenerated, recycled, stored and vitamins and growth regulators are manufactured. The consumers of these zones are versatile in their feeding habits. 3. Plankton and nekton. These organisms move freely between the two above say fixed subsystems. They continue producing, converting and transporting nutrients and energy while responding to diurnal, tidal and seasonal periodicities. Holoplanktons tend to comprise relatively few species, while the meroplanktons being more diverse reflecting a variety of benthic habitats. Marine ecosystems. Marine ecosystem includes the saltwater mass of seas and oceans that cover 70.8% of the Earth's surface and contain about 97% of the planet's water, a volume of 1370 by 108 kilometers. 3. The average depth of oceans is 3,730 meters. Oceans strongly influence climate by acting as a reservoir of solar heat, thus, improving temperature extremes, and as the source of water which falls as precipitation, i.e., hydrologic cycle. The Pacific Ocean is the largest, 179.7 by 108 kilometers, coldest average 3.36 degrees Celsius, least saline 34.6 parts per thousand, and deepest average depth 4,028 meters. The Atlantic Ocean is warmer, average 3.73 degrees Celsius, more saline, average 34.9 parts per thousand, and relatively shallow, average depth 3,310 meters. It also has the longest coastline providing many natural harbors. The smallest and shallowest ocean is the Arctic. The Antarctic Southern Ocean shows wide variations in temperature, 1.8, 10 degrees Celsius. The Indian Ocean covers 77 by 10 degrees km, to an average depth of 3,872 meters. The volume of surface area of marine environment lighted by the sun is small in comparison to the total volume of water involved. This and the dilute solutions of nutrients limits production. All the seas are interconnected by currents, dominated by waves, influenced by tides and characterized by saline waters. Not only the seashore and banks which are the homes of many organisms but the open ocean, many hundreds of miles away from land, supports plant and animal communities of great diversity and complexity. Physico-chemical aspects of marine environment. In the marine environment, the most important physical factors which influence marine life are light, temperature, pressure, salinity, tides and currents. 1. Light. Light is a very significant factor in regulating the pattern of distribution of marine animals and it contributes significantly to organic production. The autotrophic primary producers exploit the light energy in the photosynthetic production of food for primary The autotrophic primary producers exploit the light energy in the photosynthetic production of food for primary macroconsumers of marine ecosystem. The amount of light exploited in photosynthesis depends on intensity of light and turbidity of water. For example, a 10 meters deep turbid coastal zone receives an equal amount of light energy as a 100 meters deep clear oceanic zone, but the maximum intensity at a 10 meters coastal water is greater. Light determines diurnal migrations of marine organisms, and it also regulates color pattern of marine animals. The deep sea fauna which lives in total darkness exhibit either colorlessness or uniform coloration. It is also somehow related with the development of visual sense organs as shown by absence of functional eyes in deep sea animals. 2. Temperature. The range of temperature in sea is far less than that on land. Arctic waters at 27 degrees Fahrenheit minus 2.8 degrees Celsius are much colder than tropical waters at 81 degrees Fahrenheit 27.2 degrees Celsius, and currents are warmer or colder than the waters through which they flow. Seasonal and daily temperature changes are larger in coastal waters than on the open sea. The surface of coastal waters is the coolest at dawn and the warmest at dusk. In general, seawater is never more than 2 degrees to 3 degrees below the freezing point of freshwater or higher than 81 degrees Fahrenheit 27.2 degrees Celsius. At any given place the temperature of deep water is almost constant cold, below the freezing point of freshwater. Unlike freshwater, seawater does not have a density maximum at 4 degrees Celsius, rather it becomes continuously denser as it gets colder. 3. Pressure. Pressure in the ocean varies from 1 atmosphere at the surface to 1,000 atmospheres at the greatest depth. Pressure changes are many times greater in the sea than in terrestrial environments and have a pronounced effect on the distribution of life. Certain organisms are restricted to surface waters when the pressure is not so great, whereas other organisms are adapted to life at great depths. Some marine organisms, such as the sperm whale and certain seals, can dive to great depths and return to the surface without difficulty. 4. Zonation of marine environment. Just as lakes exhibit stratification and zonation, so do the seas. The ocean itself is divided into two main divisions, the pelagic, or whole body of water, and the benthic, or bottom region, figure 7.3. The pelagic region is further divided into two provinces, the neritic, nearshore, water that overlays the continental shelf, and the oceanic provinces. The continental shelf is the underwater extension of the continent and it generally extends to a depth of roughly 125 to 200 m. The edge of the continental shelf may be within a few kilometers of the shore, or it may be several hundred kilometers from shore. From the edge of the continental shelf there is a more rapid descent, the continental slope, to the broad flat abyssal plain that underlies most of the ocean at a depth of 4,000, 5,000 meters. On the abyssal plain, there are extensive mountain ranges, or mid-oceanic ridges, some of which have tips projecting above sea level. In addition, there are very deep troughs, which drop down below 11,000 meters, below sea level. Life exists from the very top of sea to the bottom in virtually all areas, although its abundance is exceedingly variable. The benthic life zones are defined in terms of following physical subdivisions: the littoral, or intertidal zone, ice zone between high tide and low tide levels. The sublittoral extends from the low tide mark to the edge of the continental shelf, with the bathyal zone comprising the continental slope. The abyssal zone includes the abyssal plains, and the hadal zone includes any life in the deep trenches below 5,000 meters. The pelagic zone is divided into 3 vertical layers or zones. From the surface to about 200 meters is the photic zone, in which there is sharp gradients of illumination, temperature, and salinity. The region below this zone is called a photic zone. From 200 to 1,000 meters where very little light penetrates and where the temperature gradient is more even and gradual and without much seasonal variation, is the mesopelagic zone of aphotic zone. It contains an oxygen minimum layer and often maximum concentrations of nitrate and phosphate. Below mesopelagic is the bathypelagic zone, where darkness is virtually complete except for bioluminescence, and where temperature is low and pressure is great. 5. Stratification of marine environment. The upper layers of ocean water exhibit a stratification of temperature and salinity. Depths below 300 meters are usually thermally stable. In high and low latitudes, temperatures remain fairly constant throughout the year. In middle latitudes, temperatures vary with the season, associated with climatic changes. In summer, the surface waters become warmer and lighter, forming a temporary seasonal thermocline. In subtropical regions, the surface waters are constantly heated, developing a marked permanent thermocline. Between 500 and 1,500 meters, a permanent but relatively slight thermocline exists. Associated with a temperature gradient is oscillinity gradient or halocline, especially at the higher latitudes. There, the abundant precipitation reduces surface salinity and causes a marked change in salinity with depth. Thus, in the middle latitudes in particular, the two produce a marked gradient in density. Water masses form density layers with increasing depth. Because density of seawater does increase in depth and does not reach its greatest density at 4 degrees Celsius as with freshwater, there is no seasonal overturn. This results in a normally stable stratification of density known as the pycnocline. Because there are marked changes in temperatures with depth in the open ocean and, thus, with density, the pycnocline is a deep zone which is oxygen-rich, cold and comprises 80% of the ocean. 6. Salinity. The sea is salty, with an average salinity of 35 parts of salt weight basis per 1,000 parts of water or 3.5%, that is usually written as 35%, i.e., parts per 1,000. In contrast, the salinity of freshwater is 0.5%. The main salts are chloride, sulfates, bicarbonates, carbonates and bromides of sodium, magnesium, calcium and potassium. Of these salts, sodium chloride is present in maximum amount. The salinity of marine water fluctuates from place to place. The marine animal life has specific osmoregulatory adaptation for high saline seawater. The absence of many animal species in marine environment has been related to their inability to tolerate the high salt contents of seawater. Except few insects such as holobates and shortcolumbolans such as Isotoma and Sminthrus, most insects do not occur in marine ecosystems. 7. Currents and tides. Seawater is never static, and waves, currents, and tides are the regular features of seawater. All these phenomena are controlled by winds, cosmic forces and varying water densities. Most worldwide water currents occur at the surface and at great depths of seawater. These currents determine the interchange between the superficial and deep water masses, as well as horizontal movements. Both the horizontal and vertical movements of ocean water are significant, but for different reason. Within a given current, such as warm Gulf Stream, for instance, the water mass retains its identity for great distances, and the warm sea community ranges far north of what have been anticipated as its northernmost limits. In addition, the climate of terrestrial ecosystems is strongly affected by the nature of adjacent water masses. The prevailing winds blow across the ocean and are heated or cooled by the waters they traverse. In marine ecosystems, however, the oceanic current system controls the distribution of productivity of marine communities through vertical mixing of water masses. Because most of the ocean is permanently stratified, any essential nutrient that settles out of the upper layers, either as an inorganic mineral or as organic detritus, is not returned to the upper layers at the same location. This had led to such an improvisation of the superficial waters of the oceans that productivity in most parts of the open oceans is about the same as that of desert, because of the very low concentrations of nutrients, especially phosphorus. At the same time, the lowest waters of the ocean are nutrient-rich. There are certain regions in the world, notably at the west coasts of continents and in subpolar latitudes in both hemispheres, where deep currents rise to the surface. These are called zones of upwelling, and even though their waters are very cold, they are sites of intense production because of their relatively high concentration of nutrients. Nutrients are then cycled back to the rest of the ocean via surface currents. Tides are water movements which are caused by some astronomical factors, i.e., due to a pull by moon and sun. They represent the rise and fall of water, and often waves of long wavelengths characterize the process. The chief astronomic force behind the tidal rhythm is the attraction of the moon and sun, which depends on the movement of Earth in relation to the moon and the sun. Tides influence the seashore fauna variously, as low tides expose the shore and high tides flood the substratum. Tides. Marine coem unis. The sea biota is not abundant but contains well-marked diversity. Every major group of algae and almost every major group of animals can be found somewhere in the oceans. The only striking omissions are the vascular plants and insects, which are abundant in estuaries but which have few or no marine representatives. Communities of marine environment includes 1. Producers such as phytoplanktonic diatoms and dinoflagellates, green algae, brown algae, red algae and kelps. 2. Consumers such as zooplanktons, benthos, nekton and neuston and bacteria. The marine biotic communities can be studied separately for different life zones of the ocean as follows. A. Biotic communities of oceanic region. The oceanic region or pelagic zone is less rich in species and numbers than the coastal areas, but it has its characteristic species. Many of these are transparent or bluish, and since the sediment-free water of the open sea is marvelously transparent, these animals are nearly invisible. Animals that are too thick to be transparent frequently have smooth, shiny and silvery bodies which make them invisible by mirroring the water in which they swim. Further, the animals of the pelagic zone of ocean encounter stable and uniform environmental conby are single quote m of the waters of the sea. This equals 1. O globigerina. This equals the pelagic plankton includes diatoms and dinoflagellates. Floating stage. The figure certain holoplanktons of Zooplankton of pelagic zone. Includes representatives of every major phylum and most minor phyla. Includes representatives of every major phylum and most minor phyla, either as permanent members of the plankton community, holoplanktonic forms, or as transients during their larval stages, meroplanktonic forms. Common among permanent planktonic forms are the foraminifera and radiolaria, arrowworm, sagitta, certain annelid worms, swimming snails, jellyfishes, and most abundant of all are the crustaceans such as shrimps, copods, and cladocerans. Among the temporary zooplanktons are the larvae of large animals from all marine environments and even some freshwater environments. For example, in the zooplanktons of inshore water of Mandapam, South India Prasad, 1956 reported following animal species: flagellate protozoan Noctiluca miliaris, larval forms of colindrates such as Planula, Ephra, Semper's larva and Cerianthus larva, medusae of certain colindrates such as Bougainvillea, Obelia, Charybdea, Rhizostoma and Rhopalina, ctenophores such as Chlorobrachia and Barrow, larvae of many culichate annelids and annelids such as Tomopteris, Alciopa and Autolytus, several species of chaetognaths such as Sagitta and Spadella. Heteropod and pteropod mollusks such as Carinaria, Pterotrachea, Cleona, Chryses, larvae of echinoderms such as Bipinaria, Ophiopluteus, Echinopluteus, Auricularia, Tornaria of Balanoglossus. Species of copods such as Acardia, Calanopia, whip-like tail Labidocera, Centropages, Lumina. Sharks. Certain fishes such as tuna, shark, sardine, mackerel, herring, bonito, and anchovy live near the surface. Those fishes which occur at greater depths are often bizarre and unlike any fish found at the surface. They tend to be small, 15 to 20 meters is large for the ocean deeps, and they are exceedingly dispersed. Many have luminescent appendages with which to lure prey, or mouth that looks too large for the rest of the body. Food is not plentiful in the deep waters of the sea, so these fishes must go for long periods of time without food, and then consume as much as they can when they have a chance. Male fish 2% edrilightness. Figure 12.3. Fishes of the deep water of the ocean. Eat biotic communities of abyssal benthic zone. The abyssal benthic zone or deep sea of oceanic region is pitch dark and universal absence of light in this environment excludes the possibility of any growth of vegetation or other photosynthetic organisms. Consequently, most of the deep sea dwellers depend upon the detritus, dead body and excreta of surface forms, which sink to the sea bottom while a large number of species are active predators carnivores. However, the deep ocean benthos are surprisingly diverse. Food is a little more plentiful on the bottom than it is in the deep waters of the ocean, because the bottom sediments are the ultimate resting place for all detritus raining out of the upper layers, oceanic surface and pelagic zones. The bottom of the sea is a soft ooze, made of the organic remains and shells of foraminifera, radiolaria, and other animals and plants. Sea cucumbers, brittle stars, crinoids, sea lilies, sea urchins, certain benthic fishes, and several types of crustaceans, as well as sea anemones, clams, and similar animals are all found on the bottoms of the deepest trenches. The biomass of carnivorous brittle stars is often higher than that of the detritus feeders that serve as their food source. However, their metabolic rate is much lower. The great diversity of sea bottom fauna has been related with great constancy in the physical environment of the deep sea. B. Biotic communities of continental shelf. The communities of continental shelf are both richer and more diverse than those of open ocean. Diatoms and dinoflagellates are still the most productive phytoplanktons, but in the shallower regions green, brown, and red algae anchored to the bottom may be of great importance. Several kinds of these seaweeds are harvested from rocky shores as human food or for some commercial purpose in eastern countries, USA and India. The zooplankton of continental shelf are generally the same as in the pelagic region, but some purely pelagic species have been replaced by neritic species, and the overall diversity is somewhat higher. The temporary zooplanktons are much more abundant over the shelf region than in the open ocean. The nectins of the neritic sea are both diverse and well known. The significant nectin species of the region are large squid, whales, seals, sea otters, and sea snakes. The most numerous nectinic forms, of course, are the fishes, which include many species of shark as well as herring-like species such as menhaden, herring, sardine and anchovy, cods and their relatives, such as haddock and pollock, salmon and sea trout, flounder and other flatfish such as sole, plaice and halibut, and mackerels, including tuna and bonito. Communities of seashore or intertidal zone. The littoral, intertidal or eulittoral zone, is the region of seashore which exists between the high and low tide lines. The region of the high tide mark is called supratidal or supralittoral zone. The region of low tide is called subtidal zone. Davenport, 1903, has divided seashore or intertidal zone into submerged zone, which is the portion of the shore below the low tide exposed by very low tides, Allour Beach occupying the area between the mean low tide and mean high tide, and an upper beach which is reached by the highest of high tides. The intertidal zone is the most variable zone in the entire sea. It is completely covered at high tide, and is completely uncovered at low tide except for tide pools. Any organism that is to survive in the intertidal must be either resistant to periodic desiccation or able to burrow to water level. For example, intertidal polychaetes escape desiccation by resorting to a tuberculous mode of life whereby they can resist desiccation by retaining sufficient moisture till the occurrence of the next wetting. Barnacles can survive desiccation by remaining in a state of suspended activity during dry periods. Many plants of seashore contain jelly-like substances such as agar, which absorb large quantities of water and retain it while the tide is out. Further, the majority of shore animals utilize oxygen dissolved in water, and when the low tide exposes them during the periods of drought, they utilize the oxygen stored in the blood plasma, e.g., Nereida renicola. Barnacles achieve this by enclosing an air bubble between the shells. One of the notable characteristics of this region is the ever-present action of the waves. Therefore, the organisms living on a sandy or rocky beach have had to evolve ways of resisting wave action. Many seaweeds have tough, pliable bodies, able to blend with the waves without breaking, while the animals either are encased in hard calcareous shells, such as those of mollusks, bryozoa, starfish, barnacles and crabs, or are covered by a strong leathery skin that can bend without breaking, like that of the sea anemone and octopus. Many sedentary shore animals, e.g., sponges, tunicates, etc., have special modes of adhesion which keep them firmly attached to the substratum. However, animals of sandy beaches escape wave action by taking burrowing mode of life, because these habitats lack a hard substratum for the attachment of the animals. 4.